All right, welcome back. Gonna hit the last example for this portion of the notes. Remember, we were looking at examples of how to apply Faraday's law to a variety of situations where magnetic flux changes. That's the idea of Faraday's law. When you have a changing magnetic flux, it will create an electric field in space, and if there's a wire or a piece of metal there, then the electrons will respond to the electric field and a current will be generated. And Lenz's law helps us figure out the direction that the current is created. Just to recap on Lenz's law, let's say that this magnetic field here was increasing. That means the change in flux is with the magnetic field. You point your right thumb in the opposite direction, so you point your thumb down this way, curl your fingers, and we would get current going around this way. Now, when you have current going around a loop, it creates a magnetic field. If you curl your fingers in the direction that the current flows around the loop, your thumb points in the direction of the magnetic field. So if you curl your fingers this way, your thumb's going to point down, and that will oppose the change. It wants to prevent this magnetic field from getting bigger, so it creates a magnetic field in the opposite direction. Okay, Lenz's law. Most of the time, you'll use Faraday's law to figure out magnitudes and Lenz's law to figure out directions. So oftentimes, the negative d phi dt is not that important in Faraday's law. We're going to look at example 4, which is where you would take this loop and instead of changing the angle, changing the strength of the magnetic field, or making the loop bigger or smaller, we would take this loop and move it in or out of the magnetic field. So that brings us to this example. Moving the field in or out. We have a rectangular loop. You can see that over at the right in your own notebook. Gives some details. It's going to the right with a constant speed at the beginning. And then it enters a region where B is out of the page. Now, before the loop enters that region, no flux in the loop. If there's no flux, it can't change. As the loop enters the region, there's going to be an increasing amount of the loop inside the magnetic field, and that will increase the flux. As the loop travels through the magnetic field is constant, and the flux will not change despite the fact that the loop is moving. As the loop exits the field, the flux through the loop will decrease, and you will get another current generated. So there's only current generated in the loop when it enters or exits the field. So our first task is determine the direction and derive an expression for the magnitude of current as the right edge enters the loop. Okay, so I drew a little, I put this down just so it wouldn't clutter up the diagram up there, but this is the loop entering. The shaded area is what has magnetic flux, and if you wanted to find the area of that, it's clearly not the entire area. The area of just this portion here would be the width of that portion times the height. The height is L over 4. This section here, the speed of this is V0. I should put a 0 there. V0. V0 times T will tell you, actually, V0 would only be the speed when it first enters the loop. Or sorry, when the loop first enters the magnetic field. As the loop enters further and further, that speed might change. So this could be its speed at any time. And when you multiply speed times time, what do you get? Distance, right? Distance is speed times time. So how far this goes in is the speed times the time. And, let's look at this chart and fill that out too. Okay, and I drew another picture there of the loop leaving. This chart is asking about what happens to the speed of the loop in these regions of space. Now, speed of the loop only changes when there's a net force on it. And out here, no force. So between 0 and L, there would be, and this is the right end of the loop, between 0 and L, there's no force. The speed would stay the same, but it's not asking us about that. We can see that out here between 4 and 5, when the right edge is at between 4 and 5, that means the left edge would be over here. It's completely out. Velocity is going to stay the same there. These three sections deal with when the loop is entering. Now, between 2L and 3L, if the right edge is there, the left edge is there. And 3L, the right edge there, the left edge there. So this is entirely in. This is entering. And this would be exiting. And of course, this is outside the loop altogether. So what do we have when the loop is entering? Is the speed going to increase, decrease, or stay the same? Well, you got to think about what the forces are. We're ignoring, I don't know if this is vertical, but we're intended to ignore any kind of gravitational force. The only force is going to be from a magnetic force if there was a current going around here. Which direction is the current going to go? To find the direction of current, you need Lenz's law. Now, as this enters, what's happening to the flux? Well, the area is increasing. That's going to increase the flux. So the increase in flux points in the same direction as the magnetic field into the page. The current wants to create a magnetic field which opposes that. So you point your thumb in the opposite direction as the change in flux. Change in flux was in because area was getting bigger. Flux was increasing. So you're going to point your thumb opposite. You're going to point your thumb out of the page, curl your fingers, and when you do that, you get a current which goes this way, right? That's the induced current in our little loop. Over here, it would go down. Over here, it would go up. Now, current will experience a force in a magnetic field, IL cross B. So on the top segment, I is to the left, so you point your fingers left, B is into the page, curl your fingers down into the page, your thumb will point down. So here, the force is going to be down into the page. These are the force magnetics. On the bottom, you point your fingers to the right and curl them into the page, and here, the force is up. On the right side, you point your fingers up. Over here, you point your fingers up in the direction of current, curl your fingers into the page, and you get a magnetic force which is left, okay? The top and bottom sides cancel by symmetry, and the net force is going to be to the left, which is the opposite direction of velocity, and so this will decrease the speed. When it's entirely inside, there is no changing flux, no current, and no force. Stays the same. When it's exiting the loop, what's happening? The flux here is decreasing. As this leaves, this area is getting smaller and smaller. So the change in flux, since it's getting smaller, opposes the magnetic field. So the change in flux points out of the page. But Lenz's law says point your thumb in the opposite direction as the change in flux. Change in flux is out. So you point your thumb in and you curl your fingers and they will go clockwise. So here, the current is this way, the opposite of what it was previously. That's the current when it exits. So you have a counterclockwise current when it enters, no current while it's inside, a clockwise current when it exits, and no current when it's outside. Now use Lenz's law. Okay. Just like last time, the top and the bottom are going to cancel. But on the top, you would point your fingers to the right, curl your fingers into the page, force points up. Notice it's the opposite direction as before, which makes sense because the current's flowing in the opposite direction. On the bottom, it would point down. There is no force on the right side because there's no magnetic field. And on the left side here, you point your fingers up, curl your fingers into the page, and you will get a force to the left. Again, the opposite direction of velocity. So here, the speed will decrease as well. So that's a good, just thinking about the problem and familiarizing yourself with how to apply the many different ways of using the right-hand rule, Lenz's law, fluxes, currents, forces, all that stuff. Our first real task here, determine and derive an expression for the magnitude of the current in the loop as its right edge enters. Remember, the area depended on the velocity, and as the loop enters, the flux increases. Use Lenz's law to find the direction is counterclockwise, right? That's the direction. And then derive an expression for the magnitude of current. Now, the magnitude means absolute value, right? So we can essentially ignore that negative sign. The magnetic flux is the magnetic field times the area. I'm going to skip over the integration of that. We've seen examples of that before. And what's changing in time here? Well, we had time as part of our area expression. So this all is t to the first power, and when you take the derivative of that, BLV over 4. Okay, pretty straightforward. And then to find the current, Ohm's law, I equals V over R, epsilon is our voltage, resistance R, that's not a radius, BLV over 4R for our current. In part B, write but don't solve the differential equation. Velocity is a function of time as it enters. So again, the forces, the sum of the forces are all from the current and the magnetic field interacting. The left side has no force because it's outside of the region. The top and the bottom cancel by symmetry. And the force on the the force on the right side points to the left. Don't get these rights and lefts. This is the right side of the loop. In fact, if you wanted to clarify that, we could say right side, the right side of the loop. And the force points to the left on the right side of the loop. So there's only one force for sigma F, and it's to the left, which is negative. That's the length of the segment on the right side of the loop. Again, if you wanted to, you could add side, so you don't get confused, times B, and that equals mass times acceleration. So we plug in for the current, BLV over 4R. The length of the right side is L over 4, B, MA, and then we just need to change A to dV dt. And I just combined stuff here. So that's our differential equation. We're not solving it. Velocity as a function of time and derivative of velocity. First order differential equation. Part C was, what's the direction of the acceleration of the loop just before the left edge leaves? Well, we already talked about that, and that's how we came to this conclusion. So to summarize, when the loop leaves, the flux is shrinking. So the change in flux is opposite to B. Right? You're going to point your Lenz's law, you're going to point your thumb in the opposite direction as the change in flux. Flux was opposite B. Opposite of opposite B is with B. So point your thumb in the direction of B. I think that was into the page. Curl your fingers. You get a clockwise current. This is similar to part C for the net force, but only the left side contributes instead of the right, because that's the side that's inside the magnetic field. If you evaluate IL cross B for the left segment, you get the net force being left, and so the acceleration is also left as the loop exits. And I just made one other note down here that once the entire loop is in the field, flux is constant. So the time rate of change of flux is 0, and there'd be no voltage, no current, no net force, only when it's entering and exiting. All right, that's that. And again, really concentrate on understanding the concepts, how to use Lenz's law, getting all your right hands straight and all that kind of stuff. Very important, can save you points, good way to set yourself apart and get a firm grasp of the concepts.